Hello everyone and welcome to the next lecture of the course ML for core engineering disciplines. In the last lecture we looked at linear regression and then we also saw how we can assign confidence intervals to the parameters in linear regression, and that was done through the use of the student's t-test and a little bit of hypothesis testing. And we had to use the t-test because the standard deviation of the model parameters were unknown. So, we were approximating the standard deviation or estimating it using the sample standard deviation. Now, what we will do is we will try to understand how we can mitigate the problem of overfitting that is often encountered in even a simple model like linear regression. So, what is overfitting and what is underfitting? We will first understand it in a qualitative way, and then we will propose ways in which those can be overcome. In a later lecture we will delve more into the foundations in terms of a mathematical manner of what overfitting and underfitting are via the help of the bias variance trade off. So, let us go ahead with the lecture. So, the concept that we are trying to understand is overfitting and underfitting of a ML model. Okay. And overfitting is a scenario when the predictive power of an ML model as quantified by its performance on an unseen test set is compromised due to overtraining of the model, which could still lead to an excellent performance on the training set. Okay. So, what is happening here is that the model, right, is overfit, meaning that you made it sort of too complex, and therefore, right, it is very sensitive to the training data. And when you are trying to use it on unseen data, right, when you are trying to use it on an unseen test set, then its performance is getting compromised, right. Predictive power of this model is getting compromised. And like I said, this is happening because the model is too complex, and in a future lecture we will discuss, like I said, the bias variance trade off, which is how this can be explained in a more theoretical manner, right. So, how would this be manifested in terms of the loss function, right. So, the loss function in this case could be very low, can take very low values on the training set, and on the other hand the loss function would have a high value on the test set, right. In principle, instead of the loss function you could also talk about the R squared value, right. You could in principle talk about the R squared value, but R squared in some cases is not very sensitive, right. If you have a lot of data, then the R square value can still approach 1, right, just because you have so much data, but in those cases the loss function is still a more accurate measure of what is really happening, right. So the loss function is able to take very low values on the training set, yet the loss function has a high value on the unseen test set, and this means the predictive power of the model is compromised, right. Now when does this happen? This happens when the model, like I said, is very complex, right. This occurs when the model selected is too complex, right, and places undue importance on a certain set of features. Right. This means that the model has too many parameters, for example. So complexity could mean that, for example, model has an excessive number of parameters, or the model architecture is too complex, right. For example, you are using something like a neural network, or you are using something like a decision tree when linear regression would work, right. And like I said, even linear regression is susceptible to this problem, and there are ways in which you can mitigate this problem for linear regression. Those are tools like lasso, ridge regression and elastic nets, which we will learn later in this lecture. So the opposite of overfitting is underfitting, right, and that happens when the model does not have sufficient complexity. So the opposite of overfitting is underfitting, and this occurs, right, when the chosen ML model is unable to capture the variations in the data. Such that it performs poorly on even the training set. Okay. So in the case of overfitting, right, the loss function had very low values on the training set, right, sorry, loss function had very low values on the training set, yet it had a high value on the test set. So that was overfitting, whereas in underfitting it has low values on both the train and the test sets, right. In this case the loss function, sorry, has high values of the loss function on both the training and test sets. Okay, and that means the R square value will likely be low, right. So likely leading to low R squared values. Okay. I hope this makes sense. So what are the possibilities that can occur when you are trying to train a model, right? The model could be too complex, and in this case it would not generalize well to the test set. This is the case of overfitting. Your model could be too simple, and in this case it won't be able to capture the variations even in the training set, right. This would be the case of underfitting. And finally the model can be just right, and in this case hopefully you get comparable performance of the ML model on both the training and the test sets as quantified by the chosen loss function. So far we have only looked at the mean squared error or the sum of squared errors. However, there are other loss functions like the mean absolute error or the binary cross entropy loss function or the Tweedy loss function and so on, and we will come across these loss functions later in this course. Okay. So let us take a simple example to illustrate, right, when overfitting and underfitting can happen and how they look like. Alright, so let us open a new page, and here I am going to draw sort of a variation between a dependent variable y and just one independent variable x, right. So this is sort of a very simple and contrived example in which there is only one independent variable x, and we are trying to see if we can capture the variation in the dependent variable y as a function of x, right. And let us say that there are some data points here, right. So these are the data points here, right, and we can have two cases, right, underfitting and overfitting. So let us look at underfitting first. So in this scenario let us say that you started out with a linear regression model, right. So y equals mx plus c, and then maybe the best fit line looks something like this, right. So this is the case of underfitting, and in this case clearly, right, the model will not perform well on either the training or the test set, right. Obviously you are going to choose some of the points as part of the training set, and maybe some of these points are earmarked for testing, right. So there can be some points maybe that you are using for testing and only some of them you are using for training, but clearly this is a case of underfitting. And in overfitting the opposite happens. You have chosen too complex a model, so instead of sort of capturing the pattern that is here, the model is way too complex, right. So it has a lot of undulations, right, and it sort of tries to overcompensate for the data, right. And in this case, right, let us say you are trying to test the model on some unseen data, right. Perhaps this is the point you took and you would have wanted a prediction around that, but because the model is so complex it is going to predict a value here, right. Obviously an underfit model could have performed even worse, and then it would have predicted this particular value. But you see that clearly both overfitting and underfitting are problems, right. In this case perhaps an optimally trained model would be something like this, and I am going to draw it with a dashed line. So this kind of a model may not do like very well, right, or so well on the training set, but at least, right, if you try to extrapolate it to a test set it is not going to fail miserably, right. Whereas the overfit model, right, so this was the case of overfitting. In this case you can clearly see the model performed excellently on the training set. Obviously it passed through each of these points, right, each of these points the model was able to pass through, right, So its performance on the training set was excellent. However, when we subjected the model to unseen test data, it started to fail miserably. So that was the case of overfitting. And the last case, right, which I drew with a dashed black line, that is the case of a perfectly fit model, or what you can call an optimally selected model, right. And this kind of a model will avoid the problems and pitfalls of both under and overfitting, right. Now this is the problem of under and overfitting in case of a regression problem. Obviously even for classification problems where you are trying to predict discrete classes or discrete variables, there as well the problem of underfitting and overfitting can occur. However, we will leave that discussion for a future lecture when we will really come to regression problems by introducing the concept of logistic regression. Okay, so let us now discuss how we can deal with this overfitting problem in linear regression. See, the underfitting problem can always be dealt with by going for a more complex model. So in case linear regression does not work, you are always free to choose a random forest, a support vector machine, a gradient boosted decision tree, or even a neural network, right. So underfitting can be dealt with by going to more complex problem, but dealing with overfitting is slightly more subtle and it involves a concept known as regularization. Okay. And in this lecture we will start by introducing 3 ways in which the overfitting problem in linear regression can be addressed. So let us go on and see how we can deal with the overfitting problem in linear regression. Okay. And we will be introducing 3 ways of doing it. One of them is called ridge regression, one of them is called lasso, and I will explain what the expansion of this short form is, and the third one is called an elastic net. Obviously there are going to be many other ways of dealing with the overfitting problem, but due to the introductory nature of this course we are only going to discuss these 3 particular type of algorithms. Okay, so let us start with ridge regression and see how it works. So why does overfitting happen in linear regression, right? Overfitting can happen in linear regression if your model is placing too much weight, right, on some of the features. So some features are assigned inordinately high weights, right. So that is when overfitting can happen, right. So what do you do in ridge regression is that to avoid the problem of the model overfitting by assigning inordinately high values to the weights for some features, we introduce a penalty for very high weighting coefficients. And when you do that, obviously your model will not be able to place too much importance on any one parameter. It will sort of have to take into account all the features, and therefore the model will generalize better to unseen data, and the model will not fail in the regions of the data set where the sort of less important features assume more importance, right, in the testing set. So let us see how this is done. So in this case, in the loss function, right. So if you remember the loss function, and I will denote this by L here, the loss function for linear regression was the sum of squared errors. So you were summing over all the data points and you were capturing the difference between the true value yi and the predicted value of the model, which was beta naught plus sum j going from 1 to p, summation over all the features xij beta j. So these beta j's are the weighting coefficients. Okay. So this was the sum of squared errors. So what you would do here is, in this case you would add a penalty function, right, that will prevent these weighting coefficients bj's from taking very high values. So you sum over all the parameters, right, j going from 1 to p and then beta j squared. Okay. So this part of the loss function, right, this is the usual loss function, SSE for linear regression. And what we have done here is we have introduced a penalty term. For some weights, to prevent some weights from being too high. Now what is this lambda that we have introduced? It has a name, it is called the regularization parameter. So lambda, and I will write it here, is called the regularization parameter. So this regularization parameter quantifies the extent of the penalty, right. It tells you how high the penalty is when some of your parameters or weights take too high values. Note that we have not included beta naught in this penalty function, and the reason for that may be obvious to you. That is because beta naught just sets the scale of the problem, and the scale of the problem could be high, right, because some variables may take too high values, some variable may take low values. So if you are trying to predict a target which has high values, then beta naught will obviously be high, and we need not penalize that particular value of beta naught. Okay. So this is the loss function, and if you look at machine learning or optimization textbooks, the minimization of the loss function can also be written in a different form, right. So you are trying to minimize the loss function, right. That is what we did in linear regression when we derived the expression x transpose x inverse x transpose y, but formally you can write it as follows. You are trying to find the optimal set of parameters in ridge regression beta hat ridge, and this is the argument at which the loss function takes the minimum value. So that is called argmin, and you are minimizing over the parameters beta and you are acting this on the loss function. Okay. So this is L, and if you do argmin of L which depends on beta, then you will get the optimal set of parameters beta. Okay. So this is one way of doing it, by writing the penalty term as a regularization parameters. There is another way of implementing it. You can add it as a constraint as well. So an alternative implementation in terms of a constraint rather than a penalty term within the loss function itself, right. So here we added a penalty term within the loss function, right. If you saw here, we added a penalty term within the loss function. However, alternatively you could have just added a constraint which put a maximum limit on the value of the sum of squared parameters. Okay, so let us see how that can be done. So in this case your beta ridge would again be argmin beta, but we would use the same sum of squared errors as the loss function, sum over all the data points I going from 1 to n, true value minus the predicted value, beta naught plus sum over the parameters j going from 1 to p, beta j xij whole squared. So we would just minimize this subject to a constraint which says that if you sum over the square values of the parameters, then that should be less than equal to t. Now again one thing you should notice is we have squared the parameters, and we have done that obviously because some beta j's can be positive. That means that your particular feature, jth feature, has a positive impact on the model, and some beta j's can be negative. That means if that feature increases, the value of the target variable will reduce, right. So beta j's can be positive or negative, so therefore we should apply this constraint on beta j squared, right. Now what we can do is we can also obtain an analytical solution for this, just like we obtained an analytical solution for plain linear regression. We can also obtain an analytical solution for this, right. So let us see how that is done. So we want to minimize the loss function, right, which includes the beta squared term. So if you want to write it in sort of a matrix form as we had done earlier, so then it is argmin over beta y minus x beta, right. So this was the error, y minus x beta transpose y minus x beta, right, that gave you the sum of squared errors, and then you have a regularization term here which is lambda beta transpose beta, right. Now here I am treating beta as a vector. So beta is essentially beta 1, beta 2 up to beta p, right. So that is the vector which is appearing inside the loss function, right. So this is L of beta, right, the regularized sum of squared errors. Now like we did for the case of linear regression, you could take the partial derivative of L versus beta and set that to 0, and if you did that, what you would get is minus 2 times x transpose y minus x beta plus 2 lambda beta will be equal to 0, right, and that would mean that x transpose x plus lambda I times beta equal to x transpose y. I encourage you to check that this step leads to the next, right. You should always try to work out things on your own, and finally if you invert this, you would find that beta ridge can be expressed analytically as x transpose x plus lambda I inverse x transpose y, right. So this looks fairly similar to what we got in the case of the usual linear regression, except for this term which obviously accounts for the regularization term, and you can see that if lambda equal to 0, this expression reduces to the usual x transpose x inverse x transpose y that we had encountered earlier, right. Now what are the advantages of doing this, right. One thing that we have discussed is that overfitting can be mitigated, but there are other advantages as well. So let us go through them. Okay. So one advantage obviously is it can prevent overfitting or over reliance on some parameters to improve the generalizability of the model. Okay. So, that is one thing. The other thing which is nice about this is this lambda, right. Now, this becomes a hyperparameter, right, and if you remember, we had introduced the concept of a hyperparameter in one of the very initial lectures, where we said that it determines the model architecture. So, in this case, lambda is like a hyperparameter, and lambda can be tuned to achieve comparable performance or best performance on both the train and test sets, right. So, it is like a hyperparameter, and the last one is actually a numerical advantage. If you see here in the usual linear regression, we have to invert this matrix X transpose X, but it is possible that this matrix in some rare cases is singular, right. It has a determinant that is close to 0 or exactly 0, and in this case it becomes very difficult to invert the matrix, because you know that the inverse of a singular matrix does not exist. But when you add this regularization parameter lambda I, it could make a singular matrix non-singular, right, and thus you will be able to compute the inverse of this particular matrix. So, if X transpose X is singular, that is X transpose X inverse does not exist, or even if this matrix is close to singular, which makes it numerically very difficult to evaluate the inverse, regularization can still enable the calculation of X transpose X plus lambda I inverse. Okay. So, this brings me to the end of this lecture. In today's lecture, we introduced the concept of overfitting and underfitting in a qualitative manner for regression problems. We said that we will understand first what this means and introduce the mathematical subtleties of the bias variance trade off in a future lecture. Then we proceeded to list 3 ways in which the problem of overfitting can be dealt with in linear regression. These were ridge regression, lasso and elastic nets, and we introduced the math behind the ridge regression concept. In the next lecture, I will introduce to you the concept of lasso and elastic nets, and we will move on forward from there. Thank you, and I look forward to seeing you next time.